Okay, there we go. So,
Thank you.
yeah, good morning, everyone. So today we have the pleasure to have Andrea Chavez. She is a PhD student at the University of Texas, El Paso, and she will be discussing the paper When Geoscience Meets Generative AI and Large Language Models, Foundations, Trends, and Future Challenges. So thank you, Andrea, for being our host today, and the floor is all yours.
Okay, thank you so much, Leila. So again, my name is Andrea Chavez. I'm a PhD student in environmental science and engineering at the University of Texas at El Paso. I am also a member of NOAA's EPP MSI CESAR 2 Cohort 3. So NOAA is the National Oceanic and Atmospheric Administration. EPP MSI just stands for the Educational Partnership Program for Minority Serving Institutions. And CESAR 2 is the Center for Earth System Sciences and Remote Sensing Technologies. I'm going to be discussing the paper When Geoscience Meets Generative AI and Large Language Models, the foundations, trends, and future challenges. Thank you so much for joining this session. Okay. Okay, so what is generative AI? So generative AI represents a growing area in AI that's capable of producing new content such as text, images, and audio. It has emergent applications in fields like medicine, finance, and geoscience. Its impact in geoscience is that it can enhance data generation, prediction, and decision making. And it also addresses complex Earth system dynamics for better safety and sustainability. On the figure I provided, this just shows an overview of how a generative AI fits within a broader AI learning method. So artificial intelligence is the broadest category encompassing all methods and technologies that enables machines to mimic human intelligence. Machine learning is a subset of AI, and it's focused on systems that learn from data to improve performance on specific tasks without being explicitly programmed for each task. Deep learning represents algorithms based on neural networks with many layers, and they excel in handling complex patterns in large data sets. Generative AI, as I mentioned right now, it just involves models that generate data resembling training data, such as images, text, and audio. And we also have large language models. These are deep learning models specifically designed to process and generate human-like text. The objective and scope of this paper was to explore how generative AI and large language models can transform geoscience. Its scope is to identify applications, current trends, and challenges. And they also highlight the potential of generative AI in supporting geoscience research and innovation. So a little bit of background on generative models. This paper does talk about 3 key models in generative AI. We have generative adversarial networks, which create realistic synthetic data by learning from probability distributions. They also mention transformers, which are a foundational model architecture that are known for their ability, for their ability to handle complex dependencies within data sequences, which enable breakthroughs in natural language processing and computer vision. The transformers have become the foundation for AI in large language models, such as GPT, which are generative pre-trained transformers, and they're used for language and imaging tasks. We also have variational autoencoders, which generate data while still encoding variability. Some history. So generative AI origins do trace back to early generative models like a Gaussian mixture model and a hidden Markov model from the 1950s. And it's been advancing with deep learning models like generative adversarial networks in 2004. In 2004, these generative adversarial networks did mark a big breakthrough for generative AI because it created a network generating content like a generative model and another evaluator called a discriminative model. And we also had transformers with natural language processing and computer vision, which led to advancements like having BERT or ChatGPT. So generative AI in geoscience, I'm going to talk a little bit of the overview of generative AI's role in revolutionizing geoscience. So some of the key applications are that it can enhance data interpretation, seismic activity prediction, and resource exploration and environmental monitoring. On the figure, this image does list how generative AI can be applied in geoscience and domains such as reservoir engineering, drilling, production, transition to renewable energy, geophysics, oil and gas, cogeneration, and energy demand forecasting. So here is a little bit more detailed how those applications domains would work in generative AI in geoscience. So for reservoir engineering, generative AI can be used in reservoir engineering to examine fluid flow, analyze well performance, and production data. In terms for production optimization, large language models can assist in providing real-time analysis of production data and also suggest adjustments to extraction rates, pressure levels, and other operational parameters. For drilling, large language models could be used to analyze geological data and predicting drilling tasks, which are important for good planning. These models can also help determine optimal drilling parameters and provide insights into drilling fluid properties and their effects on drilling efficiency. Additionally, GPT models, generative pre-trained transformer models, can help monitor drilling operations and identify possible problems as well as solutions. For geomechanics, the GPT models can provide useful information about rock strength and permeability. It can also predict potential geochemical risks concerning subsidence, fault reactivation, and induced seismicity. For code generation, these models can automatically generate programming scripts. This is possible thanks to advanced natural language processing capabilities of those large language models. And finally, also carbon emissions reductions and transition to renewable energies. This generative AI can help fulfill the compliance standards for carbon emissions by developing cleaner production processes. And in this paper, they did mention that in 2023 at the United Nations Climate Change Conference, how these carbon emissions could develop those cleaner production processes. Okay, so now I'm going to discuss three main types of generative AI models used in geoscience. So I mentioned these briefly right now. The generative adversarial networks, they're used for data generation, seismic imaging, and simulating geological structures. We also have foundation models, such as large language models that handle multimodal data in earth sciences, and they're scalable for diverse tasks. We also have physics-informed neural networks, which integrate domain knowledge and physical laws into AI for simulation and modeling. So in this figure, what it's showing is just like those popular models in geoscience, the generative adversarial networks, the foundational models, and the physics-informed neural networks. So these deep learning frameworks, they learn automatically from data by extracting information from it. The generative adversarial networks work as unsupervised frameworks, whereas the physics-informed neural networks are hybrid physics and deep learning models for modeling system dynamics and solving differential equations. And finally, the foundation models mainly focus on in-context learning by using a pre-trained architecture. And then it just links it at the bottom right into geoscience. The paper also discussed a case study called the Seismogen for earthquake detection. So the Seismogen is a generative adversarial network-based model for generating synthetic seismic waveforms. They enhance earthquake detection by supplementing real seismic data. And the benefits are that it provides training data for improved earthquake prediction models. The paper also discusses urban science with generative AI called the City GAN and the Metro GAN. So City GAN simulates urban growth and architectural features. They also mention a Metro GAN, which simulates urban structures with geophysical constraints, and its applications are useful in urban planning and city infrastructure forecasting. So the figure shown here illustrates the link between generative AI models and geoscience applications. On the left, you can see data collected from various sources in geoscience, including space, air, ground, and ocean machinery. So these provide multimodal data for model training that is then analyzed using the data from generative AI models to perform tasks in real time that are specified by a user to support geoscience research and advancements. These advancements could be in geoscience components ranging from atmospheric science, solid earth science, marine science, and planetary science. The paper also discussed generative adversarial networks for geological phases modeling. So this would enable realistic 3D subsurface models using well data and enhancing traditional methods. But they did mention that a key challenge remains in being able to accurately scale these geological features within these types of models. Another thing that was mentioned in the paper was that large language models in geoscience. So here they talk about the K2 and the GeoChat. So the K2 is just a large language model trained on geoscience literature for domain-specific queries. So it's trained on geoscience literature, and it's enabled to answer complex questions specifically to geoscience. GeoChat is a vision large language model for remote sensing, and it supports image captioning, visual interrogation, and scene classification. And the applications of both of these would be to be able to enhance and understand geoscience data, as well as assist in analysis. On this image, this figure does show an example of prompt engineering with GeoChat. So it does demonstrate how vision large language models are applied to remote sensing and other geoscience applications. So at the top, it does say multimodal self-supervised learning. These are algorithms that train various data types, such as image, text, audio, and video. And they use multidimensional geoscience data models from satellite imagery, from weather, from Earth observations and rivers. And we also have an example of that prompt engineering using GeoChat for demonstrations. On the bottom right, it says prompt engineering in geoscience. And for example, in the region-based captioning, the user is asking, can you describe the image? And it's responded by, I see several cars in a road network. They also discussed TimeGPT for time series forecasting. So the purpose of this time series forecasting model was to predict trends in geoscience, such as climate and seismic activity. This TimeGPT is a foundational model with a transformer-based architecture specifically designed for time series data. Its key features include zero-shot interference, so it handles new data sets without retraining. It also supports real-time forecasting in various geoscience fields. Now, for some of the challenges in applying these generative AI to the geoscience, some of the challenges of using this generative AI in geoscience do include limited data quality, the high computational costs, and the lack of transparency in decision making. These issues can hinder the deployment of generative AI in models and be able to apply them into these real world applications. So on this figure, I'm just talking about the comprehensive view of those challenges. So we have high computation power, generation latency, data scarcity, the explainability and trustworthiness, as well as the fake data generation and misuse. And I do want to mention generation latency just refers to the delay or the time it takes for AI models to produce an output after receiving an input. So it's just the amount of time between when a model is prompted and when the model completes generating its response, image, or another output. So these are some of those main challenges. We also have to consider the ethical concerns and risks. So in terms of fake data and misuse, it does have a potential to create misleading data, such as fake satellite imagery. We also run the risk of misinformation. So inaccurate generative AI outputs could lead to harmful decisions in critical areas, such as environmental monitoring and the ethical considerations. So the needs to safeguard or prevent the misuse of generative AI in geoscience. So generative AI in geoscience could possess risks. So it could generate misleading data. For example, in the wrong hands, it could be used to create fake satellite images or obscure real environmental changes, which would raise ethical concerns. AI generated data could also replace the same places as real satellite imagery, and this could be misused to fake the reality of the simulation to the public. So those are some of those ethical concerns and risks. The paper also discussed future directions and recommendations. So improving data quality by developing open source and high quality geoscience data sets. They discussed increasing model transparency, so being able to build explainable AI models to improve trust and accuracy, and also having collaborative efforts. So being able to have a partnership between different AI experts and geoscience. And this would be key to responsibly applying generative AI to meet real-world needs in climate adaptation, research management, and public safety. So in conclusion, generative AI is transforming geoscience and it's offering solutions for data interpretation, prediction, and decision making. Although we still have challenges, I think the benefits of generative AI are very significant. So we can see a lot of improvement as long as we consider those ethical risks, those challenges. And in terms of outlook, future development will depend on responsible and collaborative innovation. And I do want to mention again that this paper was just exploring those transformative potential of generative AI and large language models in geoscience, emphasizing the capabilities and understanding and predicting Earth system dynamics. It did discuss different applications such as using generative adversarial networks and large language models, physics-informed neural networks to improve data-limited model training. And the authors also emphasized generative AI's role in advancing the innovation of geoscience. And again, well, we do need to work collaboratively across disciplines to address like critical challenges such as climate change. And hopefully this would mark a significant step forward for geoscience. Thank you. Thank you so much for welcoming me to present. Is there any questions at the moment? Sorry. There we go.
Very nice.
Thank you.
Yeah. Uh, Let me start a discussion. I'm gonna give you an applause first, and then let me give you a discussion.
Okay. Thank you.
This is a great paper. I like it. Thank you, Andrea, for leading the discussion. Um, I am intrigued by one of the models you mentioned in there. That I actually have the paper here open. It's the LLM model for geoscience, which I would like us to talk more a little bit about it, especially if we are if we're thinking on something similar for water resources or a foundational model in our hydrology area. What do we have to do? It seems like they already started doing something. It's the K2 model, which seems to be based on ChatGPT, but seems to be fine-tuned with the Wikipedia and some other open access geoscience papers from top journals in earth science. Um, do you have an idea what type of fine-tuning method they use to train or fine-tune this model? Um, it,
So I
that
do
is,
have,
yeah.
oh, I'm sorry, I do have some notes. I did write down that the K2, it said it was an open source large language model
Mhm.
developed to overcome the limitations on general purpose models in specialized
Mhm.
fields.
Mhm.
They created the K2 by training the general purpose llama model with 5.5 billion tokens of geoscience literature, and then they fine-tuned it using supervised geoscience data called GeoSignal.
Mhm.
Then they tested on the GeoBench data set. The K2 effectively answered geoscience questions, it assisted in research, and it even generated new ideas. It
Mhm.
outperformed similar models they compared it to one called Galactica 6.7b and Visuna 7b. So
Mhm.
you had mentioned that this domain-specific large language model was a valuable tool for those geoscience researchers, but that's the only note I have in terms of that K2 model.
Mhm. Thank you. Yeah. Um, it's interesting. Um, I wonder if somebody's already designing something for hydrology or especially models. Because it seems to be like this is for general questions about geoscience, right?
Mhm.
Um, Not necessarily to do modeling of something, but to answer some questions about something, which in the end is a model, but um, um, yeah. I was also intrigued to see the Vision LLM and the Time GPT. Um, yeah. I mean, it seems like people are doing a lot of progress on this area.
I might have something to add
Mm.
if I so it's actually a very interesting question you asked, I think, which is there a hydrologic version of GPT on the way? I will answer. Um, as you guys recall, I'm working on LLMs, multi-agent LLMs for decision making in the context of natural hazard mitigation. And so up to this point, Praveen is reviewing right now. I'll hope to submit a paper soon. The point of this is the questions I've asked are a bit different. It is like, do we actually need hydrologic specified LLM version, or is it already there, but we can't really access it? My point being, the latest versions of LLMs have tremendous number of parameters and they still grow with each version. Of course, everyone's aware of hallucinations and other side effects that makes LLMs imprecise sometimes, and that makes us feel that the answers are not correct, or maybe the answers we're looking for are not there. Um, the question I want to ask is, so do we actually need some fine-tuned specialization and specifications of different domain LLMs, or is it already there? And what we need is to find the right way to access it. And my thinkings on that are, it's good. We're on this slide. On the bottom right, we see the prompt engineering part. So I have some start of a question that we can maybe use to build up on this discussion, and this is, to what extent the prompt engineering techniques we know and we use can make us access all the different pathways that exist in the LLM weight matrices. So if we represent the knowledge that's learned on LLMs while training by the weight matrices of the model, um, we can conceptualize that the knowledge is a pathway that you will start with a question or a sentence, and that matrix is going to lead you to what the model learned, and that will be the answer. So the answer to your question is following that path in between the matrices. So if we have hallucinations and if the answers are incorrect, of if we don't reach an answer, could it be that it's there, but we don't have the right way to access that? And thinking on that, are prompt engineering techniques good enough so we can access everything we're looking for in the LLMs? And so this is like an answer to those questions, in the sense that, do we actually need those fine-tuned LLMs, or is it already there in the tremendous amount of information? On top of that, I will add that I've recently tried to make a parallel between LLMs and information theory. And this can be made because what I do is I use agents LLM that are spatialized. So I use prompt engineering to define specific behaviors and specific roles. For instance, in the context of imagine you have multiple people talking about solution to a flood, let's say. I will have one be a mayor and I will have one be a hydrologist. When you do that, technically, a conceptualized view to see this is that the inner matrices of those LLM will be restrained to subspace of its general knowledge, because the model will be forced to answer to a specific behavior. In the case you present here, it will be geoscience knowledge. And I do believe that the model that will be trained in K2 and GeoChat is actually a subset of the general knowledge, more focused on this. So we have those agents, and we can make a parallel to information theory by actually, if we had the measure to do that, to measure the redundancy, the unique information that is brought up by every agent's knowledge, and also the synergy. And so my take on this is, could information theory driving LLM training be a way to actually unveil all those pathways that might be there and we cannot access, assuming that the tremendous documents and amount of information using to train LLM, I don't think the training is optimal, in the sense that of everything we try to put in that compressed view that is the LLM, there is not everything, because the training is not optimal, and I don't believe we'll one day reach that. However, most of the information should be there, and judging by the benchmarks and by the current state, it's not perfect. It's good and it's getting better, but it's not perfect. So my take is this: by splitting the knowledge of a global LLM into multiple specialized behavior, as it is done with K2 and GeoChat, I assume, and putting those model in interaction, can you actually access the knowledge that's there and we cannot access it? Of course, it's a lot of questions, and I literally just started thinking about those aspects. But I feel like there's a couple of elements here that could be useful to the discussion, and maybe to build on this presentation. That was a good presentation. Thank you.
Oh, thank you so much. Sorry, it's because I have a little dog and he'll bark. But yeah, it's definitely interesting. I'm fairly new to like the world of machine learning and everything, but it's been like a learning curve for me, and like it's really interesting. I'm really grateful to be able to even be able to like provide a presentation today, and just be able to understand more and maybe gain more knowledge from like this discussion.
I was thinking about the idea of the agent, that sometimes maybe could be even dangerous doing this way, because as in some way, if we don't have an answer in hydrology about something, maybe it's because we are not taking other fields. Maybe we have knowledge in another field that we're not using. In the moment that you are defining that, okay, I have to constrain the space to just the hydrology knowledge or the hydrology point of view, maybe we are doing the same. Maybe we are not going to get the answer because we are already constraining too much the space. So my idea is that maybe we already, if the information is there, this is exactly what we have to use. Then try to use all the information that is there and try to avoid exactly that. This trying to constrain too much because we don't know what we don't know.
So I would like to add this and then make us think a little bit more. So it seems to be that there's two lines of thought here. One that pushes for fine-tuning the LLMs, which is actually what the K2 model is doing. But the other one is Antoine's position, in which we just have to kind of filter what's already there or constrain the answers to the truth, right? To the ones that are more close to the truth and avoid hallucination. Which one of those would consume less time or less energy? Which one of those would be better if we were going to do a hydrologic model, a foundation hydrologic model, for example? And what would be the purpose of a foundation hydrology model? Would it be to do a better modeling afterwards, like to parameterize it better, to create a mesh that corresponds to the geography, to the climate of the region, to something like that, and then to monitor the performance of the model, and then perhaps to evaluate it better or validate it better? So what would be the purpose of a trained model or of a foundational model? Would be kind of a meta model on top of the other model, or would it be only adding to the modeling like in a cascading mode? I'm confused.
That's a good question, and I feel like the
Mm.
issue I see with retraining is that those LLMs, whether they're all Llama or GPT or different ones, evolve very quickly. And which one would you select to base the fine-tuning on, considering that a 2 times better model might come out in 6 months after? And I feel like it's a common question and it's a common concern in the whole state of the art for different applications, because those evolve so quickly, you would have to do it all over again. So as you said, time considering, is it worth investing 3 months of fine-tuning in GPT-4 when you just heard that GPT-4o just came out and handles those aspects better? Also, like in the same vein, I feel like it's maybe useful to talk about causal LLMs again, because there is a subset of the LLM science and information theory that gathers in that space, and trying to figure out, are LLMs causal? And if so, how can we train them to be more causal and all that? And I feel like this definitely rejoins with what's being talked today, just for the fact of physical founding and the physical component of the relevance of what's trying to be predicted there, if that makes any sense.
If I may offer a thought, what Antoine said first in the conversation made me think that we may be very ambitious right now, like trying to ask, like ideally to a large language model focused on hydrology, what's wrong or what's missing in the information we give it if we don't teach them from the beginning to adopt the data that we train him with. For example, when we create a stream flow prediction model, we give the model data of past the stream flow and ask him, well, predict or explain how the prediction works, but we don't tell the model in his training phase how much to doubt about every data point, because, well, every instrument has a precision. There's always noise that embedded to each data point, but we don't know that noise. And I don't know if there is a way to tell the model from the beginning, hey, you can doubt about this data that I'm giving you in this percentage. Like, we don't teach the model to doubt about the data, and then we to ask him like what's wrong in the data or how the data relates with all that noise embedded. Like, I don't think it's possible if we don't understand since the beginning how much of noise or other biases are embedded in the data we are using.
I have a general question for the group to think about. Antoine opened the door by mentioning information theory here. I think a lot of a lot of our discussions could potentially not go anywhere unless we ask some very basic and simple questions, such as how is information encoded into a machine learning model? So we need to adopt some kind of a paradigm or some kind of representation to think about machine learning models. And one classic one is to think of a machine learning model as being a way of building a joint probability density function associated with the data. This is a common one. People often think about machine learning models in terms of lots of weights. I don't particularly find that a very useful one, because what the heck is a weight? Another potential interpretation is in terms of thinking about how information is encoded is in terms of vectors, which are being manipulated. And that's the one which is commonly used to help explain large language models. The input information is represented as a vector, and then it's transformed through a series of operations to give you something at the end. But I think we have to think about machine learning models, and particularly LLMs, as very high dimensional joint probability density functions, which you have to condition in order to get your answer. And you condition them by giving them a prompt. The prompt can take many forms, such as saying, this is the value of one variable, tell me what are potential values of other variables. And in the case of a large language model, if it's a very high dimensional joint probability density function, then if you want to condition it appropriately, you're going to have to put a lot of care, as Antoine mentioned, into constructing the prompt, because that's essentially what's conditioning the joint probability density function and reducing from the range of all the possible answers to a much smaller subset, right? So anyway, I guess what I'm trying to say is that I really think the conversation we need to be having is, in what sense do LLMs encode information? How do they encode it? And then only we'd be able to start to answer the question is, how do we access that information, and does it make sense?
Yeah,
Can
I
I can
agree
I
with that. Yeah,
yeah
sorry.
sorry can
Go
I
ahead, go
ask
ahead.
like a can I ask a general question because it's a little bit unclear for me is like are we talking about generally like foundation models for hydrology or specifically about LLMs, which because I do see a very clear distinguishment between them because I'm not sure LLMs can be used as a foundation model for modeling. They could have different usages as this presentation kind of showed, but I'm not sure how exactly an LLM could be very fine-tuned or specifically tweaked to give us predictions or forecasts. And like on top of it, I'm not really sure it would be very worth of the trouble to go through that route because like these large language models were developed because of a cause, and that was primarily whether it was like military operations for decoding messages or based on this like social networks that had ideas to use and monetize them. Like what's the market of the whole, what's the total market of hydrology that we're talking about? Like what's the money being like channeled into field of hydrology, whether it's worth it to like work on it or not? That's a general question I have. So yeah, thanks.
Maybe I can complement that question with my thoughts after Hoshin's intervention. Um, so maybe one thing that LLMs can help resolve or help while doing our job as a hydrologist or our computer modelers is to provide some contextual learning to be able to better parameterize the model, better do the mesh of the model, better use the precipitation that's needed, better understand the processes, constrain some of those parameters or frameworks or whatever we're doing. And perhaps that can add and improve the model itself. So one thing would be, what's the right question to ask before you do the modeling, so the LLM can provide the best bang for the buck, so your model improves in, up to a certain level or after a certain threshold, without even starting to model. So it's what are the questions that you need to ask to the LLM so that your model improves without even running your model. And I assume there are different levels of questions. Some of them would be very basic, so don't even ask them because those you already know the answer. But if there are questions worth to ask, what would be the questions you would ask so your model already is doing better than if you do not ask those questions? That could be probably, that's, however, again, every question we ask has about something has a certain level of information that is relevant to the model. So there needs to be an order of questions or something that we need to think or create a list of, so we don't waste time asking questions that don't matter. Perhaps that's a line of thought.
Sina, since you raised the issue, what do you see as the distinction between an LLM and a general foundation model?
I think basically LLMs are specifically designed to work with text data. Like working with LSTMs, like introduced when they were introduced, that was very successful implementation of text models in the field of hydrology. I get that, but based on the trend I'm following in the climate community, I think they have used the same concepts, but they have developed models based on the ideas that using these LLMs, but they have inserted in the cohort of their own models, and they have foundation model for in climate now. But that's not my field of expertise, so someone else might comment better on it. But we have geo foundation models recently, like a foundation model for satellite imagery classification was developed, which was trained from scratch on image data. So the concepts of training and the concept of design were similar, but it was not really related to text and not prompt engineering. So it was a general foundation model, a very large global or regional model, I could put it. That's something so I think what Hernan commented was, I get it now, that we could use these large language models for asking very good questions. They could give very good insight how to improve our models, but I don't think they will be able to do the modeling for us. On the other hand, Geo foundation models will be able to do the modeling themselves. So we could have very complicated models which use different tools or modules to handle the stream flow or whatever the process we're interested in. But once again, one thing that I'm super interested in is that, and this is something is a little bit ambiguous, is we know that hydrology is local, like the processes are local to some extent, but to this point, a lot of research has proven that based on the information theory you talked about, Hoshin, that if we put more data into the models, encode them, the encoder will use that information to give us a better representation, and that global representation has been shown to be more useful compared to basin-wise comparison. So also just to finalize it, I do think that the training approach and fine-tuning approach, even if we have these models, is also some important thing to consider.
Well, whether it gives us a better representation or not remains to be seen.
Yeah.
But the reason I'm asking my question, Sina, is that I think we have to be careful when we use the word language. Because the colloquial interpretation of the word language is something like English, Chinese, Japanese, German, whatever. And then you ask, why do we construct language? What's its function? And I would argue that its function is partly communication, partly to enable reasoning, which is why you have grammatical rules. Those grammatical rules have to be followed. Without those rules, you can't do reasoning. And partly to help establish relationships that describe the world. So partly it's descriptive, partly it's about logical processing or reasoning, and partly it's about communication. And if you accept that that's true, then when you go back to information theory, you start with an alphabet from which you construct a dictionary of words that have certain meaning, and then you construct grammatical rules for how you process that information. If you view it from that perspective, every domain science is a language. And so the issue is what are the grammatical rules that you are learning by processing that information, which allow you or enable you to do reasoning based on establishing relationships amongst various things in there. What's the alphabet? What's the dictionary? What's the set of grammatical rules? And then on top of that, we might add language in the colloquial sense, in that in order to access all of that, we have to use natural language, because that's the language that we speak, right? So that's the sense in which I'm trying to understand the structure of what's going on. Yeah.
You give me a very good thing to think about. So I have to think about what you just said. But just a quick question. If we consider like what you said, like even like our modeling approach, like a language, but we know like in climate science and hydrology, we are working with stochastic processes. Do we have stochastic processes in general languages as well? Because I do have seen like people have been working on like using these large language models for stock prediction, which is a stochastic process in general. And I'm not saying they haven't been successful, but it hasn't been really like a massive success. So that's one of the reasons I kind of a little bit doubtful how successful it could be in our field. So yeah.
But I would argue that when I'm talking to you, I'm a stochastic model generating a string of words. And you can't predict exactly what word I'm going to give next. It depends on a number of factors, partly random and partly based on my conditioning and my training and so on and so forth that brought me. And similarly, if I ask you to start from the same word, I give you the first word and I say the, and you've played that game where you then each person adds one word to the thing and you generate a sequence, right? So presumably when we're playing that game, we're following some of the rules of language, but there's a stochastic element to it. If they're not successful at predicting the stock market, I would argue then that the problem is one of, have you learned the correct underlying relationships and so on that would enable you to do that prediction? That's why I was saying it remains to be seen whether our current machine learning architectures are capable of learning the correct architectures. That was my question. Yeah. And people keep proposing novelties, new forms of architecture. So you started with artificial neural networks with fixed weights, and then we learned convolutional neural networks to process a particular kind of information. Then we learned LSTMs to process information with memory, and you could argue that switched from fixed weights to context-dependent gates. And then we learned transformers, which said, yes, we need to do context dependence, and the context dependence depends on the order of the sequence of things that's being presented. The question is, what's the next realization we will have about the underlying architecture that needs to go in? Yeah.
Ocean, you've pointed me to a few like transformative papers. Do any spring to mind that is a reading suggestion for sort of this whole idea of different languages and grammars and how this is all a very general problem?
Unfortunately not. I think I've seen one talk given where a person alluded to the fact that we're learning grammars and language. I haven't seen much else along that, which is why I've been more intrigued. Most of the talks are coming from machine learning people, but I'm if anybody runs across some work where they're bringing an information theory perspective to it, I think that's interesting, right? Because I think that that's helping us to understand the underlying what's actually going on underneath, right? And I just happen to be dragged in the direction of saying that information theory is about learning languages. It just happened to be the direction that I got dragged. But no, I'm sorry, I don't have something to point to right now.
So back to one of Antoine's points, I admit I still kind of struggle with synergistic information, but I think I'd agree, and maybe though I come from a different angle, but I'd agree that information theory is pretty essential to the evaluation of a general model like an LLM. And I haven't got into synergy, but redundancy is a fairly like straightforward one. And you mentioned causality, and there's different definitions of, what is causality. Causality is physics truly causal, all this. But I think it's safe to say a causal model is one that just is very, generalizes very well to, conditions that sort of are vastly outside of the model training set. And so this is important for LLMs. And, I'll use an example of, say, a planetary motion. This is the sort of the classic one in causality and machine learning. But if we have a LLM that's, just trained on the observation motion of the planets as seen from Earth, it will develop a very good predictive model for the locations of the planets. But if we add maybe like, one set of observations from Mars to that, I don't think, how LLMs are currently constructed would kind of like account for it. They would still predict planetary motion, like a sort of a geocentric model, right? But what they need to account for is sort of the redundancy. We have all of these redundant observations. And so, but now we see something that's like drastically different, and that we need to weight that differently as we update our information about the world. So redundancy, causality, information theory are definitely topics I'm also interested in, and I'm glad to hear other people thinking about them.
Antoine, if you had to give a definition of why we should consider something causal, what would that be?
This is a hard one.
Mm-hmm. I mean, my take is that there's at least some issue of locality involved. In other words,
Yeah,
spatial and temporal proximity have something to do with it.
is it fair to say that there is always causality? It's just a question of how many factors do you consider?
Well, I mean, you're dealing with the decomposition of the difference between, everybody has been talking about this correlation and causal, right?
Yeah.
And the only thing that I can come up with for causal is that something to be causal, it has to have occurred prior in time, first of all, and that typically, unless you take into account quantum effects, which are kind of causing people to question physics, if you leave that out, it seems to have had a connection through some kind of local spatial effect, right? In other words, if something happens very far away, we typically don't think of that as causal unless there's a chain of events connecting that through space and time to the current point.
Yeah, I think that was sort of my point with what chaos says. Like, is it a good vision to consider that at some extent you have a lot of parameters, and saying it's causal actually means you can apply a threshold that you will go over, saying that the different vectors are too far away or too low in probability to actually have caused this, but in theory it would not be impossible.
They say causal is something which we apply as an explanation for something when we say the probability approaches so close to one that we may as well call it one.
Yeah, that's the definition I like. Very, 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 very strong correlation.
To the point where it's non-replaceable, right? Yeah.
Yeah, as for the as for the questions we raised on language and all that, I'm looking it up right now. I'll dig a bit more, but when I was in bachelor and master's degree in Université Paris-Saclay, I had a lot of professors of computer science from different instances in Orsay, and one of those I feel like is called LIPN, which is computer science applies to language sciences or something like that. I'm gonna dig it up and see if I can find old professors' work on subjects I like. I mean, I had multiple classes on compilation theory and how you actually create and structure a programming language. And writing a compiler is mildly difficult if you know all those concepts. You can structure grammars, and there are multiple steps of lexical analysis, grammar analysis, and semantic analysis for compilation and linking. That goes back to C and like old-ish languages. So formalizing language, simple ones, is not new. It's not news. But I feel like structuring and describing the human language definitely. So the point would be how would okay, let me rephrase this. As for causal LLMs, in the pursuing of some specialization like hydrology foundational model, for instance, whether it is generative or LLM, would fine-tuning with causal benchmarks or custom defined grammars that describe something you'd like to learn would be a good way to fine-tune models in some foundational perspective.
Hi, I'm so sorry for interrupting. I do have class right now, but I just wanted to say thank you for inviting me to this info theory group and for allowing me to present today. I look forward to joining some other conversations and having like more input I could provide. Thank you so much. It was really nice to meet everybody.
Thanks, Andrea. The obviously your choice sparked a lot of conversation, so that was a good choice.
Um, do
Doing
I
that.
go ahead and just stop sharing, right? And then like since the Zoom meeting is
Sure.
everyone has the link. Okay. Thank you so much. Have a
Yes.
great day, everybody.
Sure.
Thank you, Andrea.
Thank you.
I can't remember everything you just said, Antoine, but I'll just mention a couple of things that come to my mind. One is I don't think it's an accident that Shannon was particularly interested in the structure of language. Right. I mean, information theory grew out of his interest in the structure of language, and he was the first person to try to look at conditional probabilities for predicting next words, and that was what all of this entropy stuff came out of. That's one thing. But I tend to suspect that we haven't yet sufficiently exploited this concept of compression and understanding what exactly happens when we do compression as a way of understanding what's going on. And I think machine learning in general is not exploiting the notion of compression yet, except for some people like Marcus Hutter and others who are really pushing that as the basis of artificial intelligence. So I'm curious to see what will happen as more and more pressure starts to be brought to bear when, because of energy or computational power or storage or whatever, we start to realize that we have to be more efficient in the way we build models. So it occurs to me that, for example, causality is a sort of an explanation that I think we come up for the world because we need to compress our experiences down and represent them in a way that is kind of reliable, right?
Yeah, as for what you just said on compression, I think I talked about that in this discussion group. I'm not sure though. But at some point for a hydrocomplexity class, I was conducting a project on dynamical systems and LLMs. And I was trying out some smaller models because, as you said, compression is a big topic. And even though ChatGPT 4.0 is incredible, not anyone can run this on an on-premise machine. You need a cloud, you need to access something. So I leaned in onto smaller models, open source one developed. For instance, there is a Python. I think it's a Python package. Actually, it's called OLama. And it's very cool. It's linked to a database of open source models you can just download weights from and start using them very easily on premise. Usually those models are up to 7 billion parameters maximum. After that, you might need to go into the 32 gigs of RAM to run them, whatever. So I tried a couple of small models that are said to be specialized on different topics or at least minimalistic. There is one developed by Microsoft, it's called Phi-3, and the small versions of that had the one that gave me the most compelling results, even though not not perfect. And that links to what representation you were talking about, or if the LLM knowledge can be represented as PDF, condition on and all that. So basically, I conducted a very small, simple experiment. I built a small code, totally independent, so the code would reset every time and the instance of the LLM too. And basically, I had a very simple prompt, which is I roll a dice and the output is, and expecting for an export prediction, and ran that for 20,000 times, which is quite fast when you're running the model on premise with that small model. And it was some sort of a surprise, but we're not very far from a uniform distribution. I ran the same experiment by saying, so a small prompt pattern, which is a few shot. I say, I'm walking in the street. I ask this person IQ, it is 90. I ask this person IQ, it's 110. I walk in the street still. What is the IQ of this person? Ran the same thing, and it is definitely a bell-shaped curve. The tails are offset into non-reasonable numbers. But and as for the shape, it starts to look good, and that is a very, very small model that is meant to be specified on a more mathematical formalizing capacity rather than full language and full semantic. Of course, it's able to answer simple questions, but it's so my take with that is there are small models that are capable of some specific or specialized tasks. And that is, I guess, part of what motivates me into trying to split the knowledge. It's the divide to conquer method. Or instead of having this huge monolithic model, everything tends to prove to us that maximizing the unique contribution to everyone and bringing people together is what makes it work. All the assemblies and this discussion right now is everyone's got its own specificities, its own unique contribution, and this is the fact that these people are brought together, that sparks a discussion and creates interesting results. And for all this time, we've been using the LLM as a monolithic element. That's sort of what we call the oracle in the computational theory. The oracle is something omniscient that you use to theorize a comparison to Turing machines and stuff like that in state automating theory. And why have we used that thing in a monolithic fashion where we could split the knowledge specificities and making them interact? And I just remember that, but that phi-3 experiment with the very simple distribution out of a description of a use case was interesting in my opinion. So I mean, whatever happens, I'll keep developing in this way in my own research, and I'd be glad to share results and where that goes. But yeah.
I think you're absolutely on the right track, Antoine. Leela, I think the one topic that we really should perhaps adopt as a group sometime in the future is transformer architectures and dig into them, because we're using this term LLMs, large language models, but really the machinery behind them is transformer architectures. And if you look at transformer architectures, they have this concept of attention, and then they have this concept of multi-headed attention. And what's multi-headed attention, if not an ensemble approach to processing the same information? And if you take your comment a little further, why would you not build an ensemble of LLMs, which are like multiple independent personalities that have to somehow, I mean, psychologists tell us that we're not single unified personalities. We're actually multiple independent personalities internally with some kind of a mechanism which sort of takes all the different perspectives and blends them together, and you know, comes up with a decision process. So I like you know, it's sort of like the blind man and the elephant, each having slightly different perspectives of the whole. Somehow you construct a better image of the whole by not building a monolithic entity, but building a cluster of some kind, right? Sort of makes sense. If you take that a little further, you could say that we all speak multiple languages also. Right.
And it's interesting what Hoshin is saying. It's exactly what ChatGPT, when you ask a question, he gives you the ChatGPT gives you two options, and then you can pick whatever you like the most. But at the core, those are the same answers written with different words. So if you take the random forest approach, you would end up averaging them and then kind of creating a better answer for those. And I can imagine they can give you as many answers as you would like to hear. But the core still be the same. I mean, and one other thing I was going to say before, yeah.
Before you go on, Hernan, don't you think the interesting thing about random forest is not the average, but the distribution of answers that they give us?
Yeah, that's interesting, because that makes things more generalizable, perhaps, and less bias. And you could keep asking questions and it'll give you 10 answers. It's like a decision tree that opens and opens. And then you can actually create a forest of answers and then come up with something. Another thing I was gonna say is that I was gonna say something that this was related with the Sina question. When I actually play with the Google Colab, and when you ask it, they already run Gemini. When you ask a question about a problem that you have and you wanted to create a model, you can actually ask it to give the best pre-trained model that exists for that job. And so, for example, if you want to use ResNet for convolutional neural networks, you can ask it to create me already a pre-trained model with the weights pre-trained for that task. And it already gives you something that's better than if you don't have if you don't ask that question. So you start from asking a question, then you have a pre-trained model that you can actually train the top layers with your data. So that's kind of my point from the beginning. Can you use an LLM to start from nothing to boost your model before you even begin the modeling? And the other question would be, how can you then use that LLM to track the progress of the model? And actually, at the end, how can you use it at the end of a model to validate it or to help better train it or parameterize it or something? Yeah, I think that's kind of your that's gonna be your area, Luis, in the near future. Yeah. All open questions.
The closest metaphor to what you just said, Hernan, that I can think of is the AlphaGo team. When they started, they were training their model to basically, they started by giving it the rules, and then later on they allowed it to learn the rules by interacting, and then they allowed it to learn the rules for playing many games. And sort of the direction it's going to is essentially a generic thing, which you don't have to give it anything. You just have to give it the environment, and it starts interacting with it, and it learns the rules directly. Obviously, I mean, that would be like, why do people come to your class to learn to take a particular subject, right? They could just go out and learn it on their own, but you're giving them some kind of a set of rules to start with or operate on. And unfortunately, those rules might be wrong. But yeah, that just sort of speaks to the general structure of learning. Yeah.
If I may ask, if I am following the conversation correctly, would that require that for each type of different data that we want to use as information, then we will require the model to know a new set of rules? Like if we are giving it time series, then we will need to constrain or give them a physical sense of what the limits are, the thresholds. But then if we want to also use satellite images, then we will need to tell them how to interpret that kind of information. And then we will be speaking or telling them how to speak multiple different languages as data type we have. Is that what will be required?
Let's take an analogy. If I give you only time series data, and the only rule I give you is that you have to compress. That's why I like compression as a metaphor so much. If the only rule I give you is you have to compress, you're going to have to learn something about the underlying structure of the data to allow you to compress it. If I give you only images, no time, and I ask you to compress, you're going to have to learn something about the underlying spatial structure of the data in order to compress it, right? Now, in the case of time series analysis, we started out by saying we're going to look for particular patterns, and that was called feature engineering, right? Where we told it what patterns to look for. That's the hypothesis side of things. And then eventually, and so that was also with images. You started by saying, you look for this pattern, you look for that pattern, you look for that pattern. But eventually we concluded that no, we're not going to do that. We're going to let the machine learn the patterns by itself and figure out which are the important patterns. I think that's sort of related to your question, right?
Mhm.
But in order to do compression to learn those patterns, unfortunately, I'm going to need a lot of examples to learn a general pattern, right?
Right.
So if I do feature engineering, I give you the structure in advance, you can learn very quickly. But if I don't give you any rules at the beginning, and I just show you a chessboard, and I just show you people playing the game of chess, it's going to take you a while to figure out what the moves are and what's allowed and what's not allowed. And actually, you won't even know what's not allowed because you'll never see examples of what's not allowed. You have to figure out what's not allowed.
Exactly.
Yeah, for
So
me,
this is oh,
no, go ahead.
so this is a comment on the parallel between label type training supervised and emergent features of unsupervised. And what so I guess like with LLMs, what's funny is that the number of labels integrated in the inner structure is tremendous. I think it might help your question, Leela, but you can like have a very simple example. What I use in my model for extracting data, well, to ease the extracting of data, as I ask another LLM instead of blank one to take the previous message and extract with JSON so I can parse it very easily with code after that. And depending on how much rules I give as for the properties of the JSON and the maximum size of some stuff, the results can be quite different. And sometimes they're interesting and sometimes they're not exactly what I'm looking for. And in that particular case, specifying your own structure, basically, when I have an agent speak, I ask, okay, do a JSON with that, where you have multiple properties. One is for the content, one from and to, which is who's talking and who are you talking to, and also like different things. And in my own case, I figured it's more efficient if I do specify this structure. However, I've tested different ones. CSV, some different representations, some different things, and LLMs do know a lot as this day how to. And what's funny is like eventually when you reach slightly compressed structure, those structural patterns emerge. Like sometimes if I say do a JSON with that text, the 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 text will be summarized as content, and the from and to will be easily extracted as different properties, and the overall text amount will be significantly lower. Yeah, it's just my comment on that. I mean, it's if you want to actually try it out, it's so easy. Just like pick a text or a poem or something, send it on ChatGPT, and you can ask for different representations and different ways for that model to manipulate your data. And actually, maybe you could come up with like a good measure pertaining to information theory of how to measure that compression related to the structures and to the different interactions measured in there. And eventually with numerical data too. I feel like just with ChatGPT on the web, you can conduct like some good insights.
Antoine, have you played with 1-bit or what do they call them, 1.3-bit LLMs or not?
Oh, 1.3? I don't think so.
Call them 1-bit LLMs, but they're really like 1.3 or something because they have three options, -1, 0, and 1 for the
I haven't not. I'll
no.
look into it.
Yeah, somebody, I think it was a Chinese group, did this where they restricted the parameters of the weights to be only one of three values, 0, 1, and -1. And they trained it on the same corpus, and they found that they could the models train much faster. They use much less space. They actually function less fast because they don't have to do matrix multiplications, and they gave supposedly answers just as good as the regular LLMs, which I find kind of intriguing because that sort of suggests that everything can be represented by on-off switches, which is what we do actually in computer science. So.
Yeah, I think related to that, I think it's related. I've seen multiple compressed versions of LLMs, what they call quantized, 4-bit quantized, 8-bit quantized, stuff like that. I think it probably is the same where the weights are reduced to a certain number of possibilities.
Except in this case, they're actually reduced to being only one of those three values, not even well, quantized so far that you only had integer values, right? Yeah. I didn't want to say this while earlier, but I'm not sure I actually got a lot out of that paper when I read it. It was sort of a survey, and it kind of told me what I already knew. So I'm curious if anybody got anything interesting or surprising actually out of. Did they actually say anything that changed the way you thought about anything?
Same feeling.
Really? Yeah.
Yeah. In fact, in some moment I said, this sounds more like I don't know, magazine information that you can find something that is very general, nothing specific. So, yeah, okay. I know where they are going to submit that, but
There was a list of all the problems, and they're kind of like things that if we sat down, we could have come up with also, right? Yeah. But I'm not sure. That's why I'm asking if anybody else found something interesting there that added to their knowledge. I actually went back and looked at the survey paper they cited, and I had the same feeling about that one too. So.
I guess for me that I am not super familiar with generative AI, then it was more like a broad introduction to what you can do with this type of models in geosciences. So I guess, yeah, but yeah, not going into very many details, right?
So, okay. I guess 2 weeks from now, is that right?
That's right. And yes, our next session is going to be the final one of the year, surprisingly. And yeah, it's going to be in 2 weeks before Thanksgiving. And yeah, that's the last one before our winter break. And so Hoshin is going to be talking about Kolmogorov-Arnold networks, CANs. And yeah, if you have a session in AGU, please let me know. I'm gonna talk with Manuel, and probably we're gonna put together again a list of our sessions so that we don't miss each other in AGU.
Cool. So yeah, so I offered to talk about CANs just because I think it's interesting to understand what's going on under the hood. But I do think we should probably dig into some of these other architectures also if we can get people interested in, like I do think transformer architectures are poorly understood. And it would be interesting. Sina, you've dug into them a little bit. But anyway, I do think we should dig into them a little bit and try to understand or try to make metaphorical associations with things we do understand so that we can
Yeah,
try to find what
this
they
is a
really
very
do.
good point. This is a very good point, especially since there has been like a lot of evidence that decoder only transformer perform better for a time series analysis. And I feel like even though we've like whether it is on Kumar Research Group or in this discussion, we've mentioned it multiple times and tried to explain it, but I don't feel like the takes and the whole explanation is still like very clear. So I guess it rejoins what you're saying right now. That yeah.
Cool. Okay, good. I'm glad you guys agree. You agree, Sina? Is that worth digging into?
Yeah, absolutely. Especially I I have worked, I a little bit have been exploring with cans, and honestly, like they didn't give me at least a very superior performance compared to uh uh regular, like a very dense network. So
And I don't think, well, I'll save my comments for when I talk about them because I think there are very strong similarities and that we can talk about. And then hopefully we can say, okay, under what circumstances would one make more sense than the other? In what sense are they really the same? In what sense are they different? And actually, it's sort of interesting to go back and look at what was Kolmogorov's theorem, actually. What did it
yeah,
actually tell us about the structure of stuff, which I think is interesting to talk about. Yeah. Okay.
yeah.
We'll see you guys in a couple of weeks then. Thanks, Lita.
Sure.
Thank you, everyone. See you
Thank
next
you.
Take care,
Have a good
everyone.
day.
Bye.
All right. Bye, guys.